This video will cover the learning targets about isotopes. Both I can describe isotopes and use them to calculate the atomic mass. So this is a very new concept for you guys, probably. We understand that the numbers on the periodic table, we can figure out how many protons and neutrons and electrons something has. But here's what's kind of crazy. If you had a sample of carbon, okay, like a big bag of carbon, let's say just 100 atoms of carbon, and you started pulling out carbon atoms one by one and seeing how many protons, neutrons, and electrons they had, you would find every single carbon atom has the same amount of protons, right? Protons is what determines what the chemical identity of that atom is, and electrons would be the same as protons, that's what keeps them neutral, but all the different atoms potentially are adding up to have different masses. Okay, so you might pull out one carbon atom and be like, oh, well, this has 6 neutrons. And then pull out another carbon atom and say, oh, this has 7 neutrons. So 2 carbon atoms that have this same atomic number, right, same number of protons in the nucleus, but they have different numbers of neutrons. Okay, it's very normal. Every single element has different isotopes within their samples. So an isotope is just the idea that the atoms are identical in terms of their nature because they have the same number of protons, but they have different mass numbers. So they have different overall total masses. The example on the screen is hydrogen. Hydrogen actually comes in 3 potential forms. One form, hydrogen, just has a proton in its nucleus and an electron on the outside, and that's it. Okay, so that would have a mass number of 1. But then there's heavy hydrogen, which we call deuterium, which has 1 proton in its nucleus still, right? That's its identity, but has a neutron. So now it has a mass number of 2. Tritium hydrogen, which is another form of hydrogen, has still that 1 proton, that's its chemical identity, but now it has 2 neutrons for a mass number of 3. And all 3 of these have similar properties in that they are exhibiting as hydrogen, but because of their numbers of neutrons, their nuclei is different masses and potentially different in terms of its stability. So that tritium is radioactive. Okay. An analogy I like to think of sometimes with isotopes, because it's a weird concept for people to think about, is like pasta. Okay, if I said pasta to you, a lot of people in their brains would bring up an image of that long, skinny spaghetti noodle, right? Spaghetti is a subset of pasta. But there's lots of different forms of pasta, and if we threw them all in a bag and started pulling out one by one, we would pull out a lot of different ones, and they might have all different masses, and they might have slightly different forms or slightly different properties that you could measure, but they're all the same. They're all made out of the same fundamental thing, making them all the same in terms of their pasta-ness. Okay. You can do this with humans even. We got tons of humans, right? Throw them all in the bag, start pulling them out. Each individual human would be considered an isotope, right? Fundamentally, we're the same. We're made out of the same structure, but individually, we have slightly different properties. And that essentially is how we describe isotope. So the main misconception here is for people to say well, what is the carbon atom versus carbon's isotopes? And that's not a thing. Okay, an isotope is just a way of describing that when you have a sample of any given element, you have multiple different atoms in there with different masses, and they are all isotopes of one another. So you have a most common isotope, but they're all isotopes. So there's no common carbon atom and isotope carbon atom. All forms of carbon are isotopes of one another. So why does this matter? Well, this matters because we've been talking about mass number, right? Where if I have 6 protons and 6 neutrons, I'd have a mass number of 12. Well, when you take a sample of carbon and mass it, you don't get 12, or you don't get a nice, perfect, rounded whole number. You get a fraction, you get this decimal point. And we go, why? What the heck is going on that I don't get a nice mass number? And that's because that number on the periodic table, that's not mass number, it's called atomic mass, that is an average of all of the occurring isotopes. So that if I had a sample of carbon and could mass it, what I would get there is an average of the mass numbers, not a specific mass number. Okay? So a lot of people probably have heard of carbon-12 with radioactive dating. When we date things using carbon, we're looking at carbon-13. Carbon-13 has those 6 protons and 7 neutrons. Okay? So the fact that isotopes exist, that we have multiple masses of the same element, means that you have to have an average mass. Now, it's not just an average the way you often think about an average. It's what's called a weighted average. So what a weighted average does is it gives you information in terms of what the most abundant or common isotope is. So for example, for chlorine, if I had isotope 35 and isotope 37, a regular average then for those two isotopes would be 36. But if you look at your periodic table, you'll see that the actual atomic mass of chlorine is much closer to 35. And that's because chlorine 35 is more abundant. So we give it more weight. Even with the carbon example on the screen here, common isotopes of carbon, carbon 12, carbon 13, because the average is 12.011, you can clearly see that that carbon 12 is more abundant. It's more likely to be found in nature. Thus, when you give it its weight, when you say like 98% of the time I'm going to find carbon 12 and only 2% carbon 13, it ends up that your weighted average is different than like a pure average. Atomic mass is measured in AMUs, which is an atomic mass unit. Essentially, we give the weight of every proton and neutron a 1, and the electron's essentially nothing because the mass of an electron is so tiny. It's 1/1870th of a proton. So electrons don't affect any of this math or information. So when you think of a weighted average, it's all a question of if you started pulling atoms out of the bag, how likely are you to get a certain isotope? That's the one you give weight to. Now, how do I actually calculate those atomic masses? We can calculate atomic masses given the mass numbers of all the different isotopes within our sample and their abundance. So an abundance will be a percent. It'll be a how likely am I able to find this particular isotope in a given sample. So of all 100, how many of them are blah, blah, blah. So the way you do a weighted average is you just take the mass number, multiply them by the percents. So essentially you're getting like what fraction of that is going into the average, and then you just add them up. So for example, here's how you would set up a calculation for how to find that weighted average. You take the mass number of the isotope, so 85, and you multiply it by the percent as a decimal point. So you get what portion of that 85 is actually being contributed to the overall sample, only 72%. Then you take the 87 and you multiply it by its abundance or its percentage as a decimal point, so 0.278 to get that 24.186. And again, that's how much of the 87 is being contributed to that overall sample. To get a final answer then, you're just going to add these two numbers together. If you do that, you get 85.556. Round all of these numbers up to the 100th location, place a label on it of AMU because these masses are done in atomic mass unit, and that's it. Okay. Go ahead and try the questions on this and have a nice night.